Okay, so one of the rules whenever you have square roots, cube roots, fourth roots, whatever, to put it in symbols form, you can't have square roots, cube roots, whatever kind of roots in the denominator. So the process of getting rid of that radical in the denominator is called rationalizing the denominator. You're trying to turn the denominator, the bottom, into a rational number. So look down at the bottom. It's a very simple case. And the simplest case is I just have something like the square root of 3 in the bottom. Just multiply the top and the bottom by the square root of 3, and then poof, it disappears. Watch. So I get to multiply the top and the bottom by the square root of 3 over the square root of 3 because that's just a fancy 1, right? Square root of 3 divided by square root of 3 is just 1. Fancy way of writing it. So multiplying straight across, you get 5 square root of 3, and on the bottom, square root of 3 times square root of 3 is just 3. So that simplifies as 5 square root of 3, all divided by 3. It may not look simpler, but we prefer it that way. That's the way we conventionally write square roots and stuff. Okay, so process, well, let's see if it's the same whenever it's, say, the cube root instead. So I have 5 divided by the cube root of 3. So let's try the same thing. Let's multiply by a fancy 1. Let's try to multiply by the cube root of 3 on the top and bottom. That makes sense. Just following the same pattern that we did before. And across the top, just multiply them together. I get 5. Oh yeah, fancy 1. Yeah, wait for that. Okay. 5 cube root of 3. And on the bottom, I've got the cube root of 3 times cube root of 3. Those don't cancel this time. I get the cube root of 9 on the bottom. And that's not simplified. It's not simplified because the 9 is 3 times 3, and so I still have, a cube root on the denominator. Okay. So let's see how we're supposed to overcome all that. All right? So instead of looking at it as an nth root, let's look at it in terms of it being a rational exponent, because sometimes just switching your perspective makes it a little easier to understand what's going on. Okay, so basically I'm going to think of the cube root as 3 to the 1/3 power. It means the same thing. And what I want to happen is to be able to multiply 3 to the 1/3 times 3 to something else, I don't know what it is, in order to get 3 to the 1st power, right? I want that. That way on the denominator of the fraction, I just get the number 3, as in 3 to the 1st power, not like the cube root of 3 or the cube root of 9 even. Okay, so over there on the left hand side of that equation I just wrote down, they have like bases, so you get to add the exponents, so that's 1/3 plus x. Okay, and this is from those properties of exponential equations, that if the bases are the same, the exponents must be the same. So this means that 1/3 plus x equals 1. I think we can solve this equation. That means x is equal to 2/3. What does that mean? That means that if you were to multiply x to the 1/3 times x to the 2/3, you get, well, you just get x back. In this case, well, we'll get 3 back. So here's what this would look like then. This would look like this. The cube root of 3 times the cube root of 3 squared, that would all multiply together to give me just 3. And that's what I'd want to happen in the denominator so that I don't have any cube roots anymore. Okay, so in general, this is what it has it stated. Okay, so in general, when rationalizing the denominator involving an nth root, you want to multiply by the root's difference from 1. I had 1/3, as in it was the cube root, so I subtract that from 1, I get 2/3. That's what I have to multiply in the top and the bottom. So let's take a look at that again with that same example, and I'll just do this one with you. Okay, so remember what we just said is that this is the 1/3 power, so I need to multiply it times the 2/3 power, which is the cube root of 3 squared on the top and the bottom. Cube root of 3 squared. So across the top, just multiply it, and I get 5 times the cube root of, and then 3 squared is just 9, over, and then the cube root of 3 times the cube root of 3 squared cancel each other out, and they just give me 3 back. And now it's in simplest radical form. I know it's a bit more challenging than the square roots, but you know, we're grown-ups now. We can handle this. We can do this kind of algebra. All right, so here it is. This is the proof of it, basically, written out in general, that if I have a to the 1/nth power times a to the 1 minus, you subtract the power from 1. Okay, the bases are the same, so you add up those exponents, and what's going to happen to these two fractions? 1 over n minus 1 over n. They cancel. It leaves me a to the first power. So again, what this is saying in general, whenever you want to rationalize the denominator, you take the exponent, whatever it is, subtract that number from 1, and that's what you're going to have to multiply the top and the bottom by. So look at this one as an example. 5 to the 1/4, so the 4th root of 5. In other words, you'd multiply that by 5 to the 3/4. Those exponents would add up to 1, and then you just get your 5 back. Okay? So here it is in nth root notation. So the nth root of a times the nth root of a to the n minus 1, you get to bring those things together, and then a times a to the n minus 1, you would add the exponents together, and you would get the 1 minus the 1, that's a to the n, and then nth root and the a to the n, they cancel each other out, just giving you a back. So let's look at that with a specific example then, and that's the same thing with the 5th root, or the 4th root of 5 times the 4th root of 5 cubed. So those things, that's a difference from 1. Multiplying them together, poof, everything disappears, and I just get 5 back. Okay, so let's practice rationalizing some denominators right here on exercise 6. Okay, so I'm going to say that what you definitely need to do is simplify radicals before you do this. It'll make your life a little easier. So for example, this 250, let's go ahead and factor tree that thing, because that is, let's say, 2 times 125, not 2. That's, whoops, okay. 5 times 25, which is 5 times 5. And this is cube root, and look at that, I just happen to have 3 factors of that 5 in there. So first of all, this will simplify as 5 cube root of, what do we have left inside there? A 2 over the cube root of 3. Okay, so I need to get rid of the cube root that's on the denominator. It's the 1/3 power, so I need to subtract that from 1, basically, and multiply this by the cube root of 3 squared. The cube root of 3 squared. Okay. Hi, Rob. Come on in. Let me finish up this problem, and then I'll help you out, all right? Okay. So across the top, I'd have 5 cube root of, and then you can go ahead and multiply out the 2 times the 3 squared, 3 squared being 9, 9 times 2 is 18, over, and then what's going to happen with all of these, the cube root of 3 times the cube root of 3 squared, that's just 3. And there you go, that's in simplest radical form. Let me take care of this kid, and then look at that number 2. All right, okay, so we just did number 1, so let's finish up here with the number 2 one. Okay, so let's see what happens if you don't simplify first. Okay, so I would break this up as the 4th root of 10 on the bottom and the 4th root of 27. 4th root of 10 on the top, 4th root of 27 on the bottom. And then I'd go, oh, you got to subtract that away from 1. So this is, I got to multiply 4th root of 27 cubed. 4th root 27 cubed, top and bottom. And yeah, this totally works. This totally works. And in other words, I'd get the 4th root of something over 27. That something is, I have to look it up here. 196,830. And then you'd have to simplify that. And who wants to do that? So, instead, let's look at that 27 simplified. So the 27 simplified is 3 and 9 and 3 and 3. In other words, it's 3 to the 3rd. So I'm going to come back down here and make this 4th root of 10 over the 4th root of 3 cubed. And now you can see that all I need, I see I have 3/4 basically now. In order to get up to 1, all I need is 1/4. I just need to multiply this by 1 power 4 to the third on the top and the bottom. So 4 to the third, multiply across the top, and I get 4 fourth root of 30 over, and now this is going to be the 4th root of 3 to the 4th, and we know those things are supposed to cancel out, so I get the 4th root of 30 over 3. So that's what this whole thing is supposed to simplify to. So that's what happens if you don't simplify your radicals first. So factor your radicals before rationalizing the denominator, and then what you're going to do is still subtract the powers from 1 so you can see what you're supposed to multiply the top and the bottom by. So another example here, I have 1 over 5, 5th root of 9. So factor it first as 1 over the 5th root of 3 squared. So I have 2/5. I need to subtract that away from 1. I need 3/5. So I'm going to multiply the top and the bottom of this by the 5th root of 3 cubed, top and bottom. Okay, so then I multiply the top, that's 5th root of 27, and then 3 on the bottom. Okay. So that, again, kind of tricky. I think you can handle it though. Show me you can handle it on these two problems right here on exercise 7. Pause it and give those two a try. All right, here we go, and see if this matches what you came up with. So on the first one, you definitely want to simplify or factor that 8 that's in the bottom as 2 cubes so that you can subtract those from 1. I got 3/5, so I need to multiply by 2/5 on the top and the bottom in order to make it disappear. And then over here on number, so you get the 5th root of 28 over 2. Okay, over here on number 2, whenever you separate the two 5th roots, the 4 you want to factor is 2 squared. And then, so you have 2/5, so you'll have to multiply it by the 3/5 on the top and the bottom in order to get rid of the radicals on the bottom. So you have the 5th root 24 over 2. Okay, just a little bit more. This part is the easiest so far. Okay, so adding and subtracting radicals. Adding and subtracting radicals is just like terms. Okay, you can only add or subtract radicals if they are like radicals. This means they have the same index, or the same index and the same radicand. Okay. So you treat those things like they're a variable, and you just add up or subtract the coefficients of those things. All right, it's a piece of cake, watch. So for example, on number 1, I've got 7 5th roots of 12 minus a 5th root of 12. I've got 7 of them, and I take away 1 of them. They are the same radical, 5th root of 12. I get just 6 of them, 6 5th root of 12. And of course, if you could, you'd simplify that 5th root of 12, but this one won. That's it. That's all you got to do. Okay, so this still works with rational exponents. So notice that these two things are exactly the same. So I just have 4 of them plus 8 more of them. I have a total of 12 times 9 to the 2/3 power. It's very, very easy. Okay. And then it looks like I can't do anything on number 3. It doesn't look like they are like radicals. So first, let's try to simplify these. Let's put them in simplest radical form. So this is 9 and 9, 3 and 3, and another 3 and a 3. So that makes a 3 cube root of 3. Now let's do this on this one. This is 3 and an 8, and this is a 2 and a 4, and a 2 and a 2. So you have 3 of those 2's, so minus 2 cube root of 3. I have 3 of them, minus 2 of them, that gives me just 1 of them, a cube root of 3. So that one was probably the trickiest of the bunch because you actually had to simplify the radicals beforehand. Okay, so give these just two simple problems a try. And let's check our work, and that'll be the end of this video.
So it wasn't too bad, right? Here are your 2 answers. On number 1, you want to simplify that 3rd root of 40. And when you do, there's 3 factors of 2. That gets to come out, and 5 has to stay on the inside. That makes them like radicals, so then you have one of them plus 2 more of them makes 3 cube root of 5, and that's done. Number 2 is even simpler than that. 8 to the 1/5 is exactly the same, so you just get to add those things together, add the coefficients, you got 2 of them plus 10 more of them, you got 12 total. Alright, so that concludes that one. Alright, got a little bit more left on this. I think it's the variable part. Yeah, tricky stuff. Let's tackle that next.